Good, it's 1:05. Hello and welcome again. This is our third workshop on Python and fourth in total. To be able to catch up, I have posted the link to our YouTube videos from the previous workshops. So we have our two Python fundamentals workshop already posted there. And there you should be able to find all you need to kind of rerun the scripts and redo the workshops again. And then I posted another link, which is collab.research.google.com. So if you're new to this, this is the link for accessing the Collab notebooks, which we will use for our today's and other workshops. So please, subscribe to the YouTube channel, subscribe to our LinkedIn channel, and of course, if you kind of feel this course isn't for you, you can always let us know that we should remove you from the newsletter. So for those who are the first time part of this, we are part of the Horizon NextAIRE project. It's a ERA Talents project, which aims at the capacity building in widening countries with the focus on AI and air quality. Within those, we are organizing this workshop to increase the knowledge with our partners, but also beyond in Python coding, data science, and later on air quality and sensors. So please go to the collab.research.google.com page, and I will share my screen here. Good. So this is what you should be seeing once you enter the Collab page. So basically you can start a new notebook. We will use mine here, which is previously created. But yeah, for you, it's probably a new one. Then the next thing here is our YouTube page, right? So you have the Python Fundamentals 1 and parts 2 here. If you feel kind of you have missed something, this video will also be posted in here. And now to our workshop number 4. So today we'll repeat a bit things from our previous session, and we'll add some novelties. And starting from the next workshop, which is same time in 2 weeks, we will go deeper into data science. There will be other teachers with you, but the principle will be more or less the same. So kind of following things in using Google Colab and coding alongside the teacher. So we're live code typing, and first we'll start with the recap for the functions, just to remember those, because this is an essential part of working in Python. So let's start with defining the function. Now let's remind ourselves. I will just try to zoom in here a bit. Okay, this should be visible. Let me know if kind of you don't see well, or I should zoom in again. So we want to define a function, right? So let's remind ourselves we define functions with the def, right? I have here turned on AI auto-completion, AI suggestions, right? This is an option in Python in Google Colab. And this can help you a lot, especially with advanced stuff, but for the sake of this course, we're not using this so much, right? So you see here, you can use autocomplete. If you don't have it turned on, you can use settings for turning on the AI assistance. And then here in the editor, you can also click onto some options. When you restart your work book, you can either do it by coding and executing, or by reconnecting here or connecting. This will create the virtual machine. So def, we write functions like this, right? We have a function name. We take in some arguments and we do some actions, right? This is how we write functions in general. So our first function for today is to make a decision whether the concentration of a particulate matter in the air is kind of being bad air or not. So the function is called isBad, right? With the underscore, you see how it's being colored in here. So def is blue, isBad, the function names is written in brown, and it takes an argument always in round brackets, which will be PM. PM is a variable, right? And then we can have some action, and in here we will return an output if PM is greater than 25, right? So we assume here that 25 microgram per cubic meter is not good for our health, and this is why we have set this threshold, right? So we have the inline return in here, right? We could have done it the other way around, which would be, I don't know, we can create a variable A is PM larger than 25, then return A. This was another option, right? So you Control Enter, Shift Enter the cell, and then we use the function, right? Is bad, and then we pass it an argument, which is 12 here. It says false. Why? Because this condition that PM, which was 12, is not greater than 25. It's smaller than 25, and it returned the false. If we say isBad is 42, it will return true. So this condition has been satisfied, right? And this is the same as, so you see here we have defined A and then returned A, but we could have done it a bit simpler and just say return PM is larger than 25. If I do it this way, isBad, it returns the same answers, right? So this was basically skipping a line which wasn't needed in Python, right? So you can do things in one-liners sometimes. This is convenient, so you have less code when coding. Good. This has been just a warm-up. Let's move on. What we haven't talked about so much was that we have positional and default arguments, right? So when writing functions, I will just write a random function now. You can have a couple of arguments, right? Like A, B, C, D, and return A, B, C, D. A, B, C, D. Okay, and let's test it in the same cell. Return 1, 2, 3, 4. Oh, sorry. Function. I'll remain it as my fonts. Here I have my fonts. There it is, right? So the task was to return the arguments, right? In this function, all of those are positional arguments, right? So if you write it the other way around, so 1, 3, 2, 4, right? It's returning kind of position by position. There is another option with arguments, which is defining so-called default arguments, right? So let's say that B is 2 if not given otherwise, right? So I've just created, rewritten this function. So my function is requesting two arguments, which are a and b, but b is given, right, as a default. So if I write my funds as 10 and 20, right, so it's taking two arguments, I will get 10 and 20. But if I skip the 20, right, it will return a 2 because it has to return a b, right? So we see here return a and b. But b is a default argument, meaning it's predefined, right? So whatever you, if you don't add a b, it will still return a b because it's the function's task to return it, but it's already given as a default. I can do the same thing with a, and if I write my funds without any arguments, it will still return a and b because they're both default. So you see, we have two types of arguments, and sometimes it's needed because sometimes you have a calculation where you say, okay, this is just, we can have these optional arguments, we can have default arguments, and this can kind of ease up some of your tasks. What could be a kind of real-life example of this is what we have here below, right? Sometimes, with your instruments, with your sensors, you have scaling factors, right? Because, you have calibrated and, it needs to be scaled. And in a normal situation where everything is working well, you could have a scaling factor of 1, right? So this scaling factor is defined by default, but if you need to adapt it, you can, right? So here we have written a scaling function where we're defining the function scale PM, so scale particulate matter concentration, takes in two arguments. One is a positional argument, the other one is a default argument. And then the scaling factor is, and then the scaling factor is multiplying the PM concentration. And this is what gets returned. So if we run this function and type in 20, we'll get 20, right? So I wasn't defining any factor because everything is fine with the instrument and there is no need to do it. But sometimes you do have the need to do it. So it's a Friday and there was something off with the instrument. So you can basically run through your whole database, and you can define optional factors, right? So here, factor is usually 1, but I can set it to a 2.5, and it will multiply the 20 with a 2.5 factor, right? So this is a typical example of that. You can have the default arguments, you can run without them because they're given. The operation will still be executed, but if there is a need to adapt it, you can do so. A very good example of this is something which we will face later on with machine learning. So when we start modeling, you will see there are plenty of default arguments given in the models, right? I will try to load one quickly from sklearn linear, import linear regression. So I'm importing now the linear regression function, and then I'll do the help on linear regression. Okay, let's have a look. I'll scroll up, it kind of threw out all of the documentation. Okay, so if you have a look in here, I will just copy this and paste it in a different cell. Move this, sorry. And I'll have another text cell. Just paste this. So you see This part here. So linear regression has some positional arguments, and it has some default arguments. So you see, fit intercept is true. So, you know, in linear regression, following the equation of y is ax plus b, um, you actually can have the you can fit the equation without the intercept. So the default argument is here whether the intercept should also be fit, and it's true. You can change it to a false. Copy-X and jobs is, you know, if you're running a big model and you're using multiple CPUs, for example, so you can define jobs. Initially, it's none, etc. Right? So you can have, so you will see all sorts of default arguments can be given in functions. I will just add another one just to show you a more complex one. From sklearn.ensemble, you have the import random forest regressor, for example. And then I'll use help again just to see the documentation. Random forest regressor. Oh, sorry. Random forest regressor. Let's have a look at the function. Okay, so we see it in here. When you look into the documentation, so random forest is a complex algorithm, but it's fitting many decision trees, and it has all sorts of default arguments. Let's copy this line here. Okay, paste it here. For you to have a better overview of this function. Okay, so this is one of the kind of most famous machine learning models and something we will be using later in this course. But what I wanted you to see is that there are many default arguments in this function. It's a function again, right? So you don't have to define the depth of the model. You don't have to define the splits. You don't have to define the number of leaves, the number of features in the model, whether it's bootstrapping or not. You can kind of just run without it. But they are here, and you can customize this, right? So this is the reason we have default arguments and we have positional arguments, right? Good. Going further with functions, just let me know whether everything was clear with the thumb or okay, not okay, regarding these two parts, the is bad function and the scaling function, and the whole idea with positional and default arguments. Okay, I can work with one thumb up. Then we'll move on. There is another way of defining functions. All right. So in general, let me repeat this. We want to automatize our workflows. We want to speed up our workflows, right? If there is an operation which you're doing more than once, you want to write the function and you want to reduce the amount of work per data analysis per execution of your code, etc. An example can be, right, you're loading in data from your sensor and you know there has to be some smoothing or there has to be some outlier removal, and you're doing this constantly on a daily basis, hourly basis, or whatever, you can write functions once and you can execute them multiple times. This is why we're doing this, right? So we want, if you have a pH calculation from the concentration of protons in a solution, you don't want to do every times the minus log 10 of the concentration. You want to write the function and it will calculate this for you. This goes especially if you work with large data sets and you have your kind of operations on a frequent basis. So reading in data is one good example of this. There is also the option to write functions in another way, which we call lambda. These are one-liner functions. You will see them when working with code. So you can work without them, but they're very convenient once you get used to them. So the writing style is shown here, right? So and you do this usually when you need the function, for example, once, or kind of you want to shorten your code. So arguments, expression. This is the style, right? Instead of using def for the functions, you can use lambda here as the Python command. So let's try some let's test some ideas in here. So we create a function called double, and double is lambda x, right? The arguments, and then you have to define what happens with the x, and this is times 2, so x times 2. So if I run this, double is 15, right? Double of 10 is 20. So this is basically the same as def double x return x times 2. Right? This is the same thing, but now we have a one-liner. So instead of writing a multi-liner, we have now a one-liner with a very simple design, right? So this is doing the same thing. So if I run this cell and run double, it's the same as if I run this cell and do the double again. I will get the same result. So I want you guys to try something now. Write the scaling. Square x in a lambda function. This is your task, right? Square x in a lambda function, and write it in the traditional way, right? With def. So please try both. I just want to make sure that we can move forward with lambda to the next chapter. So square x is the task, and then paste your solutions in the chat. Okay, there is a solution in there. Let's try this. So square of 5 there works, and then let's test this one. Square of 5 works. Okay, I'll just write here old, and here I'll call it old as well. Works. Okay, the other option would be to do this. So 2 times asterisk and then a 2. This is also an option for squaring. Good. Seems to be working. Let's move on to list comprehensions. This is often deemed as something which is a bit abstract, but it can be a very useful thing, especially when you work with tables and you want to change, for example, the column names in your table in Python. So list comprehensions apply an expression to every item in a list. So let's remember lists first, right? So let's do lists. So a list is a collection of data. No, 1, 2, 3, 4. Right? This is a list. If I print it, here we are. If I check the data type of a list, it's a list. So this works, right? So list comprehensions apply a function or an action to every item in a list in one line, right? So what would be a common approach, right? For item in a list, print item, okay? Or if you want to square an item, then you would do maybe items square, right here. You see from 1, 2, 3, 4, 4 item in a list, print items item squared. Right? And then we see from 1, 2, 3, 4, we got the 1, 4, 9, and 16. Okay, but now we want to write it with this new style with list comprehension. So we have created a new list, which is readings. So readings is a list of 3 items, 10, 20, and 30. So please create this list of readings, or you can give it any other name as well. Good. And then we want to double or square each item, right? So the style is there is an expression within a list, right? We're still within a list. We're creating a new list for every item in an existing list, for example, right? So you see here for X in readings, that means for every item in this collection, it has to do something. And the expression here says square it, right? Square every X for square an X for every X in readings. This is the expression. So let's test this. So to define readings first. And there it happened, right? So these were the readings. I will just print them here, 10, 20, 30. And now we want to square each. So square every X for X in readings. But I can also go beyond that. I can use functions I maybe had from before, right? Let me check if I have the function double. I had the function double, you may remember it. It was defined above, right? We had it defined 2 ways here as the kind of the usual style, and then we have the lambda function. So I will just copy it down here again. So I have the function double, which says an X should be multiplied by 2, doubled. So for every PM value in readings, and these are these ones, so 10, 20, and 30, double it, right? Double is a function which takes in an argument, and the argument is the same one from from the for loop in here, right? So it takes the PM for every PM in readings and does something with it. So this is doubling it. We could also use the scaling function. Scale. We know that scale PM has a default factor, right? So what it did here is it scaled it by a factor of 1. Let's try if this works. Now I have added the other argument of scale, which was the 1 by default. I made it 2.5 and I scaled every reading in readings, which is the concentration of particulate matter, by a factor of 2.5. Okay, now to see whether you got this part, do a lambda that divides each value by 1,000, and then apply this to any list. It can be the readings list. So readings, apply and list comprehension, right? And post your solutions into the chat. Sorry, my microphone was off. So we have the function divide, and it takes in an x using lambda and returns x divided by 1,000. Then for each PM value in readings, this is this list over here, it applies the divide function on each of the items. So let's test this, and this is what happened, right? We had readings, which was a list, and then it divided every number by 1,000. I could have done it to divide it by 10, for example, and then you see here we have 10 divided by 10 is a 1, 20 gives a 2, 30 gives a 3. Okay, so this is how to run automated processes on your in your pipelines and on your data. Good. Now we're moving on to working with files, and we want to understand how to read in and write files using Python. You will see in the data science module, which I think is starting in 2 weeks from now, there will be kind of more work with data, and there are very advanced functions when reading in data, and some nice libraries. But here we will do just some basics. The issue with using Google Colab is that we don't have a preloaded file system. So it's a bit different from working on your own PCs and laptops, and maybe even servers. And of course, you might be working with your offline data and kind of with servers, and also some of the sessions in this project. But for this case, we will just be creating some simple files and then reading them in. I think if you want to work in Python in the long run, you could try Visual Code. Visual Code is a free and nice tool but it's not the only one. There is PyCharm. PyCharm has some sort of community educational licenses as well. You can use this also for working with Python locally. There is Spider, there is Anaconda, and I would recommend either Visual Code or Anaconda, kind of to be installed on your PCs when working with data locally. Google Colab is very convenient for us to work online and kind of share the files with you, but that doesn't mean that we in our own work in Google Colab and kind of upload our data there. So think about trying these other options, and Anaconda is a free option as well. So please try to download it and install it for kind of any future work. Good. There is the Python function. It's a built-in function which is called open. And open has a couple of modes. It can write, W, read with an R, or append, so add stuff onto an existing file. The syntax is a bit it's a bit complex. As said, there are nice libraries nowadays, but we should still see this option before moving on to these nice libraries. So we're using open always with. So this is a function. So as long kind of the file is open, it writes, and then when it doesn't have anything to write anymore, it just closes the file. So now I will paste this into your chats, so you don't have to write all of these lines. So just copy it from the chat. And please paste this into your notebooks. So what we're doing here is we're opening a file with the name pm25.csv. So this CSV is a comma-separated file, which is a lightweight comparing to Excel, and this is something we often work with in data science. The mode we're using here is W, meaning write, and yeah, this is just part of the syntax. So as f.write, and then it writes the file line per line. So if you execute this, or if you have pasted in here, so it kind of confirms that it was written with this print statement. And then you can see this file here on the left in Google Colab, right? So you have a couple of options here, this left menu. And one of those is files. And now you see there is a pm25.csv. I will just, there's a request in the chat. Here's the link for the notebook. And I will just paste the lines again. Good, so now we have written the file, right? And the file is in here, pm25.csv. And if you double click on it, so on this pm25.csv, it should open in here. This is a feature from Google Colab that you can view the files in the menu. And this is a temporary file. And here you see these are the lines we have written in. I'll just move this around. Right, so here our first line were the headers, station date PM25. So you see in here we had a value for PM 2.5, which was 18.5. Here we didn't, right? We just had the next line in here. This is the \n. Here we had a value for PM 2.5, here as well, and then here we didn't, right? And this is what we observe in this table as well, right? For the 2nd of January 23, we don't have a measurement, and for the 3rd of January 23 in Rijeka, we also have a missing measurement. Did this work for you? Did you manage to open the file in the menu? Thumb up, hand up. Okay. Good. Okay. So now, now since we have the file, we can read it in as well, right? So with again the same command, right? With open as f. I will paste it for you as well. Content is being read in f dot read, right? We had here f dot write, and here we have f dot read. And then content is what was loaded in, and now we're just printing the content in here, right? So this is the table. It's not a nice one, but it's a table, and the file was read in, right? So to recap this, with open as something, right? And then you have the line writer, or you have the reading function, which is f dot read. Sometimes you want to read things as line by line, right? So the first part of the command is the same, with open as f, and then for line in f, so f is a collection, print line, and then each line will get printed. And this is how it recognizes the end of the lines. It's important to see these open commands, but this is not how we will work in the data science and the machine learning part. You should just be aware that you can open things line by line, especially if you're working with the sensor, for example. But if you have a dump of data somewhere, you probably won't be reading things line by line. You will use some libraries to download or access this data. And very often you have data online, right? So especially nowadays within projects funded by the European Commission, etc., all those who create data have to have them in a repository openly and freely available. And this is one of our data sets which we have there. And with that, I should show you that there is Zenodo, right? For those who haven't had the experience with. So this is a data or any sort of material repository. Doesn't have to be tabular data. It can be also for preprints, etc. And then in Zenodo you have the whole EU Open Research repository, and then you can look for projects in here. Right, so I'll just type in NextAIRE. I think should be able to find it. No. So projects. Okay, I'll search it in projects. NextAIRE. Check this again here with communities. NextAIRE. Found it. Okay, I'll try with our other project at Yaki. Yeah, this is a bit weird. Browse projects. Best match. No, they're there. Just think that the search doesn't work as it should. Another okay. Okay. No, there it is. Right. For some reason, the search didn't work as expected. But here you see, right, so for example, from the Ediaki project, we have here all the materials which we uploaded, right? So yeah, this was just one study, and then we have the data sets in here. So sometimes you can just copy the link address of this data file, and then try to load it within Python. So this should work. For this use case, I used another data set, and this is linked here, right? So with the URL, you should be able to fetch data and load them into Google Colab or in your local notebooks. Sorry for the intermezzo. Let's use a library for downloading the data. So the library is URL library, right? URL lib. URLs meaning kind of taking content from web addresses, from URLs, and we will import URL lib.request. Yes, Zenodo is free for anyone, and let me just type in here PM10. I'll just type in my name, Zenodo. Right here. Okay, this is the file we have loaded in here, right? Or one of those, right? So this is fully free, and there is a Croatian one as well. Those who are from Croatia, there is Dabar. But yeah, we're using Zenodo. It's yeah, it's kind of more present, and here you see this is the file. We have here the descriptor, and then we're using this one, right? Copy link address of this data file. If you click on it, it will offer you the download, but we're using the copy link address. I can post this one in here. And yeah, you can use it for metadata. You can use it for all sorts of things. I'm diverting now a bit from the course, but let's do this. Dissertatia. Well, this is my PhD. Second Zenodo. Okay, so I used it for my PhD thesis, for example, right? Because usually you have to burn a DVD or a CD with all of your files and add it to your thesis. What I did instead is I placed it into a repository, and then I had 9 files for my thesis, and here I kind of put some short descriptors, and here you can see the files, right? E1, E2, etc. And then in the end, I add the references where these files kind of come from or what they're related to, right? And here you see related works, etc. And then here you can see the number of downloads, number of views. I had 2 versions, and they give you the DOI code, which is convenient, and this is permanent, right? You basically shouldn't be able to remove this. This is how you can cite this data set. I have all sorts of formats for downloading it, etc. Here it says, this is published April 10. It's version number 2, and all of the files from my thesis are in here. And people use it often for metadata, etc. But back to Python, the convenience here is that we can we can find the link, find the data set which is of our interest, and then just load it in here, right? So I use it often in courses. I don't know, Zenodo, metabolites, those who are interested in, I don't know, chemistry, biochemistry, right? And then so you have some files in here which you can XSL file, right? Zip files, and then yeah, some sort of connectors, etc. So this is very convenient also for kind of working in courses such as this one. Good. So this is the library. This is our URL, which you copied from the chat, and then we have the function in here, which is your URL lib.request, and the first part from here, dot URL retrieve. Of course, these things you won't know by heart, right? And you don't have to learn them. You will probably Google for it, or ask whatever chat tool you might be using just to help you out with this. And then here is the URL. So this is my URL. This is a variable which has the address of the file I want to download, right? And then this is the name of the file I want to have once it's downloaded. And then this print statement is just to kind of show that the job has been finished, nothing else, right? I haven't defined the library. I'm rerunning this code, download it, right? So if I go to files, here you should see the data xlsx, okay? If you click on it 2 times, it will offer you the kind of download option. So you can download this file and check it out manually. But this is not something we want to do. It's a big file. We want to load it with a library. And this is a library we will use from now on, I guess, kind of in most of our workshops. It's probably the most important library to work with data. It's called Pandas. And then we're using this part just to shorten our calls to the functions and modules. So import pandas as PD. You don't have to use PD. You can use just P or pand or kind of whatever you like. Kind of convention is PD. And then there is a function which is part of PD of pandas, which is called read Excel. And as you can imagine, we have all sorts of read functions in pandas, right? So pd.read, I'll just start typing. And here you can see all the options, right? So read clipboard. That means if you have copied a file onto the clipboard and you read clipboard, it will paste what you have copied in here, right? Then you have read CSV, read Excel, read a feather file, read HTML, read JSON, Parquet, Pickle. So there are all sorts of file types, and Pandas has support for many of them. But what we want here is to read our Excel file, which is saved locally, right? It's in here. If I go to files, this is where it is. I've downloaded via the URL lib library. So this is the file. And you see the line has been executed. You see it in here. And now if you add a code cell, you can type in df. df means data frame, right? And this is also convention. You don't have to call it data frame. You can call it data. You can call it my data. You can use whatever you want. But this is just kind of a very common convention. And then you can print df, right? And this is the file we wanted to see. So our first line is actually our header, and this is counted as such. And then our measurements start, right? PM10, PM2.5, PM1, which year we're in, temperatures, etc. Then we can check the shape of this, right? df.shape. I said you will be working a lot with this one. But this one has, with this library later on, this one has 4,384 lines and 37 columns. And if you just want to check kind of the very top of it, you would call df.head, and this would show you just the first 5 lines, or df.tail, it would show you just the lower end, right? The 4,383, which is 84, because Python starts counting from 0. Right, so what we saw now, I'll just go back to this. What we saw now is that we can download a file using the URL lib library, right? This is basically how you can use Python to communicate with online files with the web, right? You can retrieve URLs using the URL retrieve function, and you can store it, right? Then you would use pandas or any other library for reading in this local file, and you would just print it to observe it. But this is something which will come in the following workshops. Today we were just about to see how to use libraries, and how to read and write data. Good. Just quickly check what I have here. Today we'll have a bit of a shorter session, and I think all the future sessions will be shorter. We won't have these 2-hour sessions anymore, because we noticed they're fairly long, and we'll have workshops every 2 weeks. So there should be enough time for everyone to catch up. Good. The last part of today's session is exception handling, which is sorry, there's something in the chat. I'm having an error. Are you working in Google Colab, Sidna, or is it local? No, that's a bit weird. Okay, can you send me your please send me your file after this session. I will just finish the session now, and then send me a file, and I can have a look at it. So you can just sorry if I haven't shown this before, here you can go to file, download, right, and then download either it's Python or is it IPYNB file, and the IPYNB is what we want here. So please send it to me after the session, and then with your email, and then I will check what it was. Yeah. Good. Exception handling, right? The reality is that you will have often errors in your code and your files, and we don't want these errors to break our workflows. We don't want them to break our code. And this is the reason why we're adding this to the kind of course plan, the exception handling. And this goes especially if you want to work with sensor data. If you want to automatically read in data, you will have errors for sure. The reasons can be all sorts of I don't know, maybe a cosmic ray hit your sensor, your semiconductor, and then you have a misreading, right? So things like that can happen, but we need to handle those within our code. So this is for handling exceptions, and the syntax is as following: try something, right? Something happens, which we deem here as risky code, and then except some error happens, and then you should have a backup plan. So this is the syntax, right? So what can be an error, and this really happens often when working with hardware, is that you want to have to convert your string or your reading to a float number. Oh, okay, you fixed it. Nice. Good. Okay, so the issue was, I guess, with the download part, not with the reading part. Yeah. Okay. I'm happy that this is solved. Going back to this, so you want to ensure that if you're converting, so this is a string, right? 18.5. This is a string. This is not a number, right? And we want to convert this to a number. If you type in type here, type, you see it's a string. It's not a number, right? But you need numbers. And one option to convert a string, if it has a number within the string characters, is to use just the float function, right? So you can convert a stringed float to a float by means of how it's defined in Python, right? So if I type in here type, just to check what the data type is, it's a float, right? It's not a string anymore. So the float function converts this to a float, the string to a float. If you would pass an empty string to this, you would receive a value error. So you can imagine now, if you have a sensor, if you have hardware, and you're reading in constantly values and writing them into your databases, you will have the situation sometimes that your hardware misses a reading, and then it shouldn't happen that it breaks the whole process. You want the process to continue regardless of this error you have there, right? So if we would have a kind of empty value and you want to convert this to a float, your whole process would be stopped at this point, right? And it would return a value error. And we want to be able to handle this using code. So this is the try except moment, right? So let's imagine we have a value which is an empty string, right? This is what we define in here. Value, nothing in there, right? So usually you have some characters in there. Now we don't have any characters. It's just an empty string, and we said here if we try, so this is the value. I will remove it here and I will just define it in here. So value is defined, right? It's an empty string, nothing else. So if I type in here some words, it will return the string as letters, it will return the letters, right? But I'm here defining just an empty string because this can happen with hardware. So if I check the data type of this type of value, it's a string, regardless of it being without any characters. So if I want to convert this value to a float, as we saw before, it will return value error. Could not convert string to float because there is no numerical values in there. Okay, so we want to turn our value into float, and if there is something wrong with it, if there is no value in there, it should not block our code from executing. So, as usual in Python, when doing these things, we have a colon. So here and here, the same was with for. loops. The same was with if-else statements. So in here, we also have the colons, and then we have the indentation. This is very typical of Python, right? And then in Google Colab, we have this nice feature. These things are being colored, so you can kind of differentiate parts of the code. So we want our value to become, to go from a string to a float, if possible. And if not, it should not return a value error, but just a none. Or we can say it's a -999 as a placeholder, for example, right? So try this, right? Try to convert value into a float, save it as PM, so assign it to PM. And if you run into a value error, which we know from here, right? If there is nothing in there, this function will return a value error. This is something we don't want to happen. We want instead, if you stumble upon a missing value or kind of an empty string, we want you to return a -999. So accept this type of error value, and then you return a 999, right? So we have our value. This is our value. Now we will convert it to a float, and if not, return a -999. Okay, and I've just printed the final PM value. So our value, the variable, was an empty string. We are trying to convert it to a float, save it to PM. If you see this is an empty string, this would be a value error. So instead, you're putting in a placeholder, which is -999. Okay, and now there is a task for you, right? So you have a value of 42.1, and you rerun this block above and see what happens. Any answers? It prints the value, yeah, because it managed. So let me add here a value. I don't know, it will be 86.7. It manages to do this part, right? It didn't raise the exception. Good. So, and this is something I do add very often to functions, because I want to have I want to avoid situations where my code is not being executed because of an error. Good. Check this part. This is just another example of this. So here I'm trying to open a file, and if the file isn't found, I want the code to return this sentence. Basically, the file is not there, right? If I open here the files, I don't have a file which is called missing.csv. So this is the part we had from before. What would have happened if I execute this without the try except, right? Let's check this, see what I get. File not found. There is no missing.csv, right? And I don't want it to raise this error. Instead, I'm writing a try except. So try to open this file, and we know it's not there. If you stumble upon a file not found error, which was this one, print file not found, check the file name. Let's execute this. See, it didn't make this mess with the error, it just returned the sentence I've asked it to. So the file wasn't there, this is what it tried, and then an exception was raised, right? Everything with the colons and with the indentations, and then it just wrote the sentence, I don't know, you can make it simpler. No file, right? No file. Okay, so this is try and accept. The next step from here is to wrap these things into functions. So if we would really be working with reading in data from sensors, we want to automate these processes, right? So this is not the code style we would be writing. We would wrap these things in a function. So the function is taking in, let's call it a measurement. Measurement, right? You can use whichever name you want. Measurement. So I want to be sure that when a value comes in from my sensor, that it goes through my function and that it creates a float from this string if the file is writing strings only. And if not, it shouldn't return anything, or it should return -999, right? So let's go with -999. This is just a placeholder. So I've defined here a function, save float. This is the function's name. It's taking in an argument, which is called measurement. And what it does, it goes into a try except situation. Try, returning the measurement as a float, as a number, not as a string. If you see a value error, don't raise the error, just return -999 instead, right? Saving this function, executing on this string here, 18.5. Works, it returned the float. Let's check this one. It returned a -999. So let's imagine a scenario where we have readings. Right, the readings are coming in a stream from a sensor, and the readings are 18.5. It's a string. I don't want the string. I want to float. Then I had the misreading. The cosmic ray hit my sensor. There wasn't a value. And then I had another valid reading. So I want for every value in readings. Let's first just print them, right? Print value. See what it did here? Print 18.5, nothing, because this reading is nothing. And then a 42.1. But this would be a problem to process in a data pipeline, right? Instead of this, I wanted to create a safe value is safe float, then it ingests the value from the readings, right? These are the values, 18.5, nothing, 42.1. And then prints the safe value. Look what happens here now. It's 18.5, it's a -999, and then a 42.1. Okay? So this is why we will be doing this, because we can't have an empty value in this data stream. We need numbers, right? But -999 is not optimal. We can change it to I don't know, a none. Execute this as well, right? And then we get a none, but none is treated as a number. So we got the none where there wasn't a value, or I can just return, I don't know, maybe you want to type this, misreading. Right here you have the misreading, because it didn't pass this part, the try except. It tried to convert it into a float, it didn't happen, and then it had the misreading. Let's try to create this function without the try except. I will remove all of these parts. Okay, I have a measurement function now, which just returns the float, right? Say float, or I can do give me float. Here's the give me float function. And I will change this to a give me float. See what happens? Can you write me what happened in here in the chat? What happened with my other values from the sensor readings? Looking for an answer from you guys. So what's the issue with this code? Or what happened in here which I don't want to happen in when working with sensors? Yeah, it's no value, right? It's so this no value, it blocked the continuation of my readings, right? It raised an error and everything was stopped. I don't want this to happen, right? I want it to continue. And this is why we had the save float function. Sorry. The save float function, I have to reread it. The save float function enabled my other readings to continue, right? This was the try except. It didn't raise the error because when raising the error with the gimme float function, everything stopped. So this shouldn't be happening. So I prevented with the try except function, with this one, save float, see try except, I'm preventing, I'll just change this to save float. I'm preventing this from happening, right? It continues with the operation regardless of the error it found in there. So this is why we want to use try except, right? So imagine where I'm using these often is when I run big models and I want, for a couple of stations or locations to run models, and it will be station wise. Sometimes something is wrong with the station, there is no data, or the data is wrong, or whatever, and I'm running a big job on a server which lasts for a week, for example. If there is a station which has missing data, I don't want it to stop with the other things, right? I just want it to skip it. So I'm building in a try except, and it says try to make a model for this station. If you can't, just move on to the next one. All right, this is where we're building in these try excepts. And just to put it all together, with all the things we have done before, I will just paste this part into the chat so you can paste it in your notebooks. So these are all parts of code we had before, right? But now we're kind of putting it together in here. So I'm importing the mean function from statistics. This is how you would usually do it. I'm creating an empty dictionary, which is stations. And then reading in the files, reading in PM25. This is the file we have in here. And then for every line in the reading, it splits this into a station, date, and a raw value. creates a safe float from the value, and then you can build in here an if statement, right? If PM is not none, then you append the data to a station. But I have an error which comes from the safe float thingy. This was supposed to be none. Like this. Okay, now it works with the none. Just go back to safe float. I will just paste it also in the chat. So this is just this is a big function, and this is something for yourself to try at home and study it. So we're reading in a file, and then for each line in F, each line in F, we were splitting the lines in three parts, right? Station, date, raw. And then we create a safe float from a raw reading. And if it's not a none value, and then if the station is not in station, then you appoint this value to a station. And then we calculate in here the mean value for each of the stations. I'll paste this line in here too. So what I wanted to show you with this is that once we know all the functions, once we know all the tricks, we can summarize these chunks of code into big code, which will do a job for us, right? So if you have to write reports station wise, and your database is somewhere else, you can write a URL lib request to read in line per line from these data, to collect them in lists or in dictionaries or JSON files, etc. And then you can do statistics per station, per pollutant, etc. Right? So we have basically seen all of this code in our 3 workshops, and it's on you more or less now to play with it, right? So Python is, as previously said, something with this runs for free. You have no cost for doing experiments. It's only about your time to kind of learn and self-learn or self-study and cause these errors to happen, so you can kind of learn from them as well. Thank you for your attention, and have a nice rest of the week.